The broadcast is now starting. All attendees are in listen-only mode.
Welcome to the PELS webinar series. Thank you for joining. Today we bring to you a PELS webinar entitled 2023 MagNet Challenge Webinar, Series Number 1, Kickoff Meeting, presented by Minji Chen from Princeton University. First, we have some housekeeping announcement. Today's webinar will be placed on the PELS Resource Center within the next week. We invite you to use the question function on your panel to ask any questions you may have regarding the content or any broadcast-related issues. Questions regarding content will be answered verbally at the end of the webinar. Information on how to request a PDH certificate has been sent to you via the chat function and will also be included in the follow-up email you will receive within 1 hour of completion of this webinar. I would now like to welcome Minji and the rest of the panelists so they can begin their presentation. We hope you enjoy the webinar. Good morning.
Okay, thank you, Megan, for a very nice introduction. Welcome everyone to this first webinar of the MagNet 2023 webinar series. We do plan to host a few webinars throughout the year to keep everyone updated about our progress and also provide a few educational sessions so that everyone is on the same page. So the purpose of this webinar is to kick off the MagNet Challenge 2023. We want to introduce you our motivation, why we are launching this challenge, and provide some information about an explanation about the rules that we set, and really try to take this opportunity to create an opportunity for all of us to know each other and really do this interesting research and education and development as a community. So first of all, let me sort of introduce our panelists today so that we all know each other and then say hi and say a few words about what we're doing. So I'll quickly go through the list and everyone on the panel can so briefly introduce yourself and say hi. First of all, I want to introduce Professor Charlie Sullivan, who many of us know has made tremendous contribution in modeling of magnetics. And about 20 years ago, he sort of launched a MagNet challenge for himself in trying to develop some models better than Steinmetz equation. That's what we're doing now. So Charlie, do you have a few words to say?
I'll just say welcome, everyone. I'm excited that there are this many people signed on and interested in this, and I look forward to your questions and to the project.
Great. So we are originally thinking Professor Johan Kolla will be joining us because he developed improved generalized Steinmetz equation, but we'll wait for him, see if he will be joining us later. Now I'll skip to next, Professor Dragan Maksimovic. So every one of us has a favorite textbook, and when you are looking for equations to calculate core loss, you go to the textbook and read it. And today we're fortunate to have Professor Dragan Maksimovic with us, who is the author of probably the best textbook in power electronics. And Dragan, maybe you want to say a few words to the community?
Yes, thank you, Minji. Hello, everyone. Really great to see this initiative getting going. And Minji, thank you for really initiating the MagNet 2023. Yeah, it is time indeed to improve our knowledge in modeling of core losses, and maybe some 10th edition of the textbook is going to include the results from this challenge. We'll see.
We don't know when that will happen. Yeah, but this is a great opportunity that someone who have a great model that really become the standards, then you can talk to Professor Maksimovic and say, hey, is there an opportunity to include your name in the textbook? So we'll go with Professor Pat Wheeler, who is a big champion of this challenge since we started the idea, and he really helped us pushing all of this through PELS and get a lot of support from the PELS administrative side. And Pat, do you want to say a few words?
Yeah, first of all, I'll apologise. I don't have a camera. I'm on a device that doesn't seem to be compatible. But I hope you can hear me okay. So I'm Pat Wheeler from the University of Nottingham. I'm also Vice President for Technical Operations for the Power Electronics Society, which is sponsoring this challenge. I'm looking forward to it. I think it's a great challenge, and I know there's a lot of very enthusiastic teams, including one from my own university. So very pleased to be here. Very pleased to listen to what's going to be said today.
Yeah, that's great. Yeah,
that's exciting times. Thank you.
Yes, that's exactly sort of like the purpose of this webinar. We hope to encourage as many student teams as possible. Thank you, Pat, for bringing that up. So Kevin Hermans is the chair of the IEEE TC10 design methodologies, and he is, again, like two of us chatted about this challenge about 2 years ago, 1 year ago, and we finally launched everything together. So Kevin, do you have a few words to say? Kevin, you're muted, I guess. All right, let's wait for him a little bit. We'll move on. So next, I'm going to introduce Dr. Thomas Guillot, who is a postdoc researcher at Dartmouth and received his PhD from ETH in Zurich. And he's really the person who is controlling the quality of our data and the quality of the model. And Tom, do you have a few words to say?
Yes, I'm actually very excited to see so many participants. I have the impression that a few years ago, this research on magnetic core modeling was a bit slow. And I really think that this last year, it's getting faster again. And I'm really excited that we have so many people today for this challenge.
Yeah, so if you have any question throughout the competition regarding data quality, if you find anything, well, how do we control the data quality? Feel free to reach out to Tom. He knows everything about how much error we have on every aspect of the data. So next, I want to introduce Xiaozhe, who is the treasurer of IEEE TC10. She also was teaming together with myself and Kevin, and we sort of launched the MagNet together. Xiaozhe, do you want to say a few words?
Yeah, thank you, Mingjie. It is really exciting to say it is finally happening, and Mingjie really helped to accelerate this process, and a lot of efforts behind it. It's really exciting opportunity. So I'm Xiaozhe Pei from University of Bath, and I'm working on cryogenic and superconductivity. So Mingjie, to be honest with you, I really looking forward to say if the model can predict how the magnetics operating at cryogenic temperatures and so on.
Yeah, that would be fun. I guess really we're trying to explore the opportunity of bringing like advanced data-driven models. And there are a lot of complex materials in power electronics, and we'll see what we learn from this challenge can benefit our understanding about other complex materials in power electronics. Then the next, I'm going to introduce Dr. Diego Serrano, who is now at UFSPID, and he was with my group in the past 2 years, and he's the person who measured all the data. So we have Tom controlling the quality, and we have Diego measuring the data and collecting all the data. So all the data we're running and supporting MagNet somewhat comes from Diego. So Diego, do you have a few words to say?
Thank you so much, Minji, for the introduction. And to all the persons attending this meeting, please enjoy this challenge.
And if there's any problem with the data, we'll have to go for that Diego. Maybe there's an error somewhere. But we tried very hard to make sure we don't have wrong label data, because for any data engineering efforts, data is the most important part. But we make mistakes. Anyone make mistakes. So if you find anything that seems wrong, there's a possibility that the data is wrong. So next, I want to introduce Haran, who is my grad student. So Haran is the person who joined the MagNet project, the first student working on the MagNet project, and then set up the automatic data aggregation system, which is a very important contribution, because without automation, there are a lot of error and we cannot collect a huge amount of data. Haran also developed a few tutorials and examples in applying basic machine learning techniques to analyzing the data, which the student teams can use as a starting point. So you can only be better than Haran if you use his tutorial. So Haran, do you have a few words to say?
Hi. Yeah. Thanks for the introduction. So it's really great to see like a lot of people here, and this is gonna be an exciting challenge in this case, and really looking forward to the great ideas and models that are going to come out from this challenge.
Great. So we have last one, who is Shukai Wan. He's a junior, the youngest grad student in my group, and hopefully will carry the torch from Diego and Haran, and he also developed a DC bias measurement circuit for the MagNet. So this year we are not going to cover DC bias because we think the data is not ready, our understanding is not ready. But in the future, there's a chance that we will include DC bias, and we need Haran to we need Shukai to collect data for us. Shukai, go ahead.
Sure, I'm Shukai. Welcome to the webinar, and I hope you enjoy the webinar. If in the future you have any more questions, please feel free to contact us, and we have our contact information at the end of the talk as well.
Great. So I think that's all the introduction part. I want to say that we intend to run the MagNet challenge as open and transparent, and we hope more people can joining us, even just collecting the data, because we feel like just my single group or with Charlie's group at Dartmouth, we're still very single-handed. It would be great if more universities can start to joining us, providing data, then we can do cross-validation. And I believe more people are starting to do this in a careful, organized way. We can improve the data quality of the data, improve the quality of the model, improve everything, and really advance our understanding about magnetics. So before I start the discussion, any other things that we want to address from the panel? No? Okay, so yeah, I intend to run this webinar as more of a discussion. So if you have any question, feel free to type in the questions. And if any of the panelists see an interesting question, feel free to interrupt me, and I'll be happy to discuss. So let's get started from why do we want to do something about statement equation? The first question is like, for every one of us, we should ask, well, do you like statement equation? And I guess the answer most of us is probably will say yes and no. We like it because it gives us really simple, intuitive understanding about core loss. We know core loss will scale up with frequency, will usually scale up with flux density. So we know it's really good equation for designers, but it can be better. So it doesn't capture a lot of factors. It's probably, if you look at Professor Maximovich's textbook, there's only one paragraph or so introducing where does this come from, and because there's no real physics behind it. It's not first principle physics model, but just a regression model based on observation. But there are a lot of limitations. There's no waveform information, no temperature information, no DC bias information, and then there's no mature way of thinking about how do we include all of these into this modeling framework. So we both need better first principle physics model, maybe just answering how do we add temperature into this framework, or maybe we develop a completely different framework so that we can add temperature, waveform, and DC bias into it. Professor Sullivan has developed the IGSC about 20 years ago, which is a great example of how a enhanced statement equation can look like. But we do hope that with the new data and more advanced modeling tools available, we can develop new understanding. Maybe curve fitting, maybe from physics, but less accurate, or maybe very, very accurate, but we don't know how it works, like such as a neural network. So from our perspective, how can we make it better? So we can think about two ways. One is we go with improving. So we stay within the statements framework. We still try to model the core loss or the material behavior and try to isolate the impacting factor. And the benefits of doing this is we can leverage all the existing explanation. There are a lot of literature, a lot of study, a lot of explanation of where core loss come from and how do we separate the hysteresis loss and eddy current loss, and how do we consider geometry impact. So there are a lot of existing knowledge that we don't want to throw it away. So there are advantage in staying within the statements framework. And on the other hand, with the new data available and new tools available, there are also opportunities in jumping outside of the statements framework. We don't have to try to feed a simple equation. Can be a complicated equation if you can explain why, or it can be a neural network where it's really just a black box that we don't really know what's going on, but it's really working, right? It's just like large language models like ChatGPT, like it works and it serves our need, give us good information. But if we dive into it, looking into parameters, we don't know exactly what it is doing. But there are ways of designing neural network that is a little bit more explainable And that's sort of where we want to reach a balance. We want to find an approach where you can get a good balance between explainability, like we can explain where things come from, and at the same time capable of capturing all of these complex factors that may have an influence on core loss. So the good thing is like now data is ready. It takes us like 3 years to get all the data and understand the complexity, understand the error. The tools are ready. We have tested a few basic neural network tools, and it seems like machine learning is working. And also Charlie has and other researchers have other advanced equation-based models, which is also working. So we have a few tools that we know will work, but we don't know if they are the best. Like it's probably far away from the best. And we need a clever mind, because we feel like with a few people we cannot try. A lot of this has to be try and error, we have to say, because it's not very, very systematic, and we're really dealing with a very complex big data problem. So that's why we think creating a community can really accelerate this process. And hopefully within 2 or 3 years, we can reach a consensus. Hey, there is a better way of modeling core loss, and everyone try it and everyone agree that this should be the next industry standard, and maybe the manufacturers and industry will pick it up and really develop from there. So that's sort of like the motivation of these MagNet challenge. Anything the panelists want to add and want to comment? No? Okay, I'll keep going. Feel free to interrupt me and jump in. So what if this will be a good question to all of us. So if we think about a winning team, how will a winning team looks like? That's the question that's going behind my mind all the time. So I would say a winning team probably should understand the physics, read the literature, and understanding what other people have done, and also look into the data carefully to see, well, what are the new information that the data is providing. So I guess a good team will have to sort of do both. The other things that it would be great if there's some material experts. Like we are designers. Myself is a designer. We don't really understand material. But if you have a colleague or if you have a friend who is doing research on thin film magnetics, so maybe some discussions like that will be very helpful, because their insight or the way they think about magnetic material is probably very different from the way we as a designer is thinking about material. But on the other hand, we can offer our insight about what kind of model would be useful, right? There are a lot of first principle physics model, which is very complicated, describing a nanoscale behavior. But in terms of components, like we don't need that information. We need a way to describe a component behavior. So really, there's opportunity for us as designers to talk about material scientists, and then really sort of leverage their understanding. And the third aspect is that, from my perspective, will be respecting legacy and challenging legacy. Like, for example, STEM education, usually as an undergrad, you won't challenge it. We'll say, yeah, this is the standard, we'll just use it. But once you become grad student, you will say, well, where does this come from? Why does it have to be this way? Where are there other supporting factors? What are the hypotheses? So I would say go read the literature and respect the legacy, because there are good reasons why it looks like that, and at the same time, don't take everything for granted. And maybe the fundamental assumption of some of those basic design rules are wrong, or it's like overly simplified. And so this is what I think will be the winning team's structure. I don't know if the panelist has any additional thoughts on how would you imagine a winning team may look like.
Yeah, so I would say one of the key would be to really try to leverage the big data set, which is something that for the past research could not really be done because this data were not existing. So a lot of the methods that have been published have been actually based on a very limited amount of data. I know that there is more data. It's really something that I would encourage you to look to see all the models. Also, the existing models are scaling to different materials, different operating conditions. This would be also a good starting point of kind of seeing what is working well on maybe what was thought to work well, but actually maybe doesn't work that well. This can also give a bit of a direction of what is most promising for a better model.
Great. Yeah. Tom is basically saying dive into the data and then really, because we as developer, we don't have the bandwidth to look into everything. So it would be great if everyone can spend some time and dive into it. And there are some interesting behavior. For example, how does the core loss change with temperature? There are interesting phenomena there, and it's probably different from material to material. It'd be great if new understanding can be developed from that perspective. Haran, do you have any comments? Maybe from machine learning side?
Yeah, so just as Minji just said, I think the winning team, the model for the winning team should like greatly well balance the model, the generality, and also the accuracy. On the one hand, we hope to have a good, accurate prediction result, but on the other hand, we hope like it has certain ability to generalize to all the waveforms. For example, in the dataset, we have sinusoidal waveforms, the triangular and trapezoidal waveforms, and also all the temperatures. And we hope like the model can be worked in a more universal operating conditions and the excitation waveforms.
Right. So Haran was talking about generality, which is very important because ultimately we want the method that was developed by the team can be applied to new material, right? So right now we provide, I'm going to introduce the details later, but right now we provide 10 materials, but it's very likely there will be 5 new material coming in with a little bit of data, not like complete data. So it'd be great if the model can be generalized so that you can learn just a little bit of information and try to predict the material's behavior beyond that. Of course, won't be always true because there could be a completely different material. So there's no physical basis of saying, hey, I can use my existing knowledge to learn the new material. But most likely in magnetics, we know where the material comes from, and the materials are similar and maybe a fine-tuned or upgraded version of the material. So it would be great if we can develop a method that can be generalized and can be used, applied across multiple materials, can sort of leverage information we know to predict information that we don't know. Charlie, do you have any comments?
Yeah, no additional comments. I think one of the hopes here is that we have ideas about what might work, but if we have lots of people with different ideas, they might win in a different way.
Yeah, exactly. Yeah, so we'll try to, I have to say that we don't, all the rules we have written in the MagNet handbook, it's not final rule, and we hope to run a competition in an open, transparent way. So if you see anything that is constraining your imagination, let us know, and we'll try to relax that so that you can try all different methods and then show the results. So Dragon, do you have any comments?
Not really. Well, maybe just to say that I wouldn't personally expect that there is a single best approach to addressing this problem. It is very likely that there are multiple, perhaps very different approaches that could have advantages in some cases and disadvantages in other. So what I'm hoping that we will get from the challenge is really this kind of wide spectrum of approaches and be able to, in the end, say what the trade-offs are overall. And maybe the trade-offs are different for different type of materials, or we'll see.
Right, this is great comments. So in the end, we will have a judging committee, including Professor Sullivan, Professor Maskimovich, Professor Kola, Professor Perrault, and Professor Longhui from NTU. So we will not only judging based on the model performance, we're also judging based on model novelty, because the most novel idea may not have the best performance, although they are related. But because the criteria is very different, like for example, model size and model accuracy, model explainability, model generality. So there are many angles of looking at the models. So we will really count on our prominent judging committee to sort of selecting the final winner of the prize. And definitely we are all very excited, and we'll try to select our best model in the end. But I have to say that we have a lot of resources. It doesn't mean that we only have one winning team. We actually have 4 winning prizes with 1 software engineering awards and many honorable mention. And we really see great models. We'll try to find resources so that everyone gets what you deserve. So yeah, that's sort of like the philosophy behind the challenge. I'll move on. So we have received a lot of support from the community, including many of us in the panel. And we also have an industry advisory committee. This is coming from Google and Tesla. When you think about magnetics and advanced data models or data science, then Tesla and Google is probably representing, Google representing data science, Tesla representing magnetics, and they are very excited to see the skill sets that student teams are demonstrating, and perhaps the winning teams can directly negotiating a internship offer at these companies. Well, you have to demonstrate that you can deal with a lot of data, and you have to demonstrate that you understand magnetics well. So we also have this ad hoc consulting committee, including many experts. They have volunteered to provide consulting services to the team. So if you think you need a external advice, feel free to, we'll release all of this information once the registration stage is finished. And then you can reach out to these consulting committee members so that they can provide their advices. And I'm sure all of us are, as researchers, we are all happy to talk about your ideas. And we have the PELS TC10 steering committee, including Kevin, Shirley, Subhan, and Miroslav. They are helping us with all the administrative side, launching this competition and get it through PELS. And finally, we have received the support from PELS signee, who sort of has put them endorsing this competition. So we thank Professor Pat Wheeler, Mario Pacas, Dehong Shi, Freddie Babloyek, and Newton Chan for signing the petition for this MagNet challenge. So I also want to mention one more thing, sort of going behind the MagNet challenge is, if you are familiar with computer vision, or if you have friends doing computer vision research, you probably heard about ImageNet challenge, which is a very good example of how MagNet challenge can be and the way how our impact can be transferred into the real world. So ImageNet challenge started from about 2010. That is when before the machine learning or computer vision becomes so popular. And that time, people are still using like feature engineering to do image detection or classification, and the error rate is very, very high. And then there's a group of researchers, actually including Professor Fei Li, who is now at Stanford, used to be at Princeton. So they started from collecting a huge amount of image, which is similar to us collecting a huge amount of data in magnetics. So they built these standard, large-scale, high-quality, well-organized image database and allow everyone to come in and look into the data and show their results and compete their models and really do apple-to-apple comparison. And as Professor McMurray said, really understanding the trade-off between different models. And then that really accelerate the understanding about image classification and computer vision, and the error rate dropped significantly within like 7 years. And that's what you see that is driven like the image detection models, and also later the large language or neural language processing community pick it up in a similar way, and they have similar database, and that's what is behind the ChatGPT, which most of us probably have heard about it. So we really see this as an opportunity for us to do the same thing within power electronics community. We want to run it as open, transparent, inclusive. We don't want to sort of like saying we know more than you do. So because everyone is doing just like at the beginning, we don't know too much more than what you do. And we're happy to listen to your thinking. And we hope that this can be a community effort which will last for a few years until we really feel that we have a mature understanding about magnetics, then we can pass knowledge to industry. I also see this as a opportunity for like community development. It's a really good opportunity for us to make friends with each other, because I really want to know, especially me and many of us want to find students who are talented in both magnetics and interested in power electronics and can do a little bit programming, right? So it's really good opportunity for us to make friends with each other. We have the similar interests and we want to develop a similar skill sets. And hopefully this will have education value, like student can learn something, everybody can get something from this competition, and we can advance research, we can have some industry impact, it could be fun, and finally it could be a rewarding experience for everyone. So we know that PELS has a hardware design challenge, and the MagNet from the administrative side will be the software design challenge of PELS. This year is magnetics, and we probably will focus on magnetics for 2 or 3 years until we switch to other topic, Could be capacitors, could be piezo materials, could be batteries. So there are many ways, or could be design control architectures. So this is really what we see as an opportunity where power electronics not just about building things, although building things is very, very important, and also building software and develop new models, and even greatly advanced computer-aided design tools in power electronics can be a great contribution to the field. We intentionally try to make these competition very low entry bar, so everyone can come in. All you need is just a computer with internet access. You probably need to know a little bit about magnetics, a little bit about power electronics, a little bit about data science, and know a little bit programming, or you know your friends and you can put them in. For example, maybe a computer science major undergrads could be very helpful in building the Python or your PyTorch software pipeline. But on the other hand, it'd be very high potential impact because this is a 100-year challenge. Like STEM education has been 100 years and they are not significant. Well, Professor Sullivan has developed IGSE and it's I2 GSE, but there are opportunities to really look into all of this from a very different way. So I would say it's very high potential impact. And maybe if we imagine 10 years or 20 years from now, there could be a MagNet GPT or Chat Power GPT, which is a software tool that can give us the information we need by just asking questions. We can say, how does this material look like at this frequency, at this temperature? And then bam, there will be a software agent telling us all this information. But now ChatGPT cannot do that because they don't have the data. So all of the infrastructures, the data we're building, the models we're developing, hopefully ultimately could be the foundation of a future really interactive design agent software tools. That could be a 5-year, 10 years tool, and we'll see how far we can do. And finally, for 2023, we have to be realistic. I don't think MagNet GPT will be realistic. It's probably too far away. What we hope is that we can have a few software package to replace the statement equation. Right now we have 10 materials. One very realistic goal is that for each of these material, we can have a MATLAB or Python callable function, and then you just put in your waveform, put in your temperature, put in your DC, not DC bias this year, but waveform and temperature and frequency information. You can get the core loss, or you can predict the BH loop. So this would be very, very useful because so far there are probably 50 active materials actively used in industry. I don't know, there probably more than that. But we don't have that many material. It's very likely we can create an open source software toolbox so that all of us, we don't need to read our database, read the data sheets ourselves. Like using our eyes to do the curve fitting ourselves on the data sheet is very inefficient. It'd be great if all of us can create a shared software package that cover most of the materials that we do in our daily life, in our regular designs, and that can greatly accelerate the design process and maybe lead to much better design. And hopefully with the result we get in 2023, the manufacturers will really start to listen and learn from what we learned through this competition. It doesn't have to publish data as image parameters. So right now, if you look at the material database, they have a few graphs and they try to curve fit the image parameter. Or if you have a software, if you look into the back end of the software, they're actually trying to give you data by applying image equation behind it. So that may not be true. So hopefully by the knowledge we created and we learned through this competition, we can slightly change how the manufacturer think about how to organize data and present data, and that will reversely enhance our design. And finally, there are many researchers here. You have your own focus in your research, and maybe this data-driven approach can be applied to other materials like magnetics, capacitors, batteries, piezoelectric. They all have this complicated multi-physics, multi-dimensional problem, and the methodologies we developed for this can be transferred to other fields. That would be my imagination, or the best result, the lowest bar. Like if you can program a image equation, you can join this competition. So your entry bar is very, very low, cost is very, very low. The potential impact is very, very high. Although I don't think we probably will achieve it within 1 year. Maybe we need 2 or 3 years or even 5 years to achieve those. And we have a few goals. If we can have let's say, one commonly used software package for the 10 materials we offer this year, that will be already quite significant achievement for the competition this year. Any comments from the panelists? No? Okay, I'll just keep going. So then it'll be a little bit more detailed. So we know STEM education need an upgrade. Why do we need an upgrade? That's a question we always ask ourselves. I guess it's a chicken egg problem. Because whenever we talk about error in magnetics, we ask for batch-to-batch variation. So we really have imprecise material. Like material quality of the material are not controlled to a way that to the accuracy level that we sometimes need. For example, for on-chip magnetics, or for in-vehicle magnetics, or in robotics magnetics, where size and volume and weight really start to matter. So a lot of emerging applications starting for asking for precision, and we actually don't have precise material, and because we don't have precise material, we probably don't need very precise model, and imprecise model lead to imprecise design. That's what's happening now, as far as I know, like in my understanding. And what we're trying to do is now let's develop a model. Let's ignore, there will be always error and batch variation on the material. There will always be application where you don't need very precise design. We know that. That's not going to change. But we can do a model which is very powerful. As long if the data is accurate, our model can really representing what the data is saying. And the model can be used to design, to apply to better design. And this sort of like break the chicken egg problem. And then we will force the manufacturer to say, hey, now there's a way to represent the material in a much better way. Can we present data in a much better way? Or we can say, there are probably applications where say, oh, you have better models. Now, really, we can reduce the cost, or we can open in new opportunities. So that's the way we think about how do we approach this. So as a result, because we don't have very precise model, we probably, all of us, throw like 20%, 50%, or even 100% margin in designing magnetics. Whether it is because of a thermal, like your converter usually work at 50 degrees C, but you design at 25 degrees C, or your converter has a saturation limit, but you don't really run there, and you don't know where exactly the material saturate, both in terms of thermal or flux density. And also batch-to-batch variation. Maybe if we have better models, we can reversely push the manufacturer so that they can sell magnetics with different grades. They can say grade A has very little variation, and grade D has large variation. You can trade the cost versus the quality of the material. So that's sort of what we see. And hopefully, if we have better model, maybe all of the power electronics, all of the magnetics can be reduced by 20% or 50%, right? If all of us are throwing 50% margin into our design, but now we have better model, maybe we only need 30% of the margin. That represents 20% volume saving or cost saving. So that could be very attractive. And we hope that the way we are thinking of this problem, I know there will be a lot of challenge, can pass a little bit to the manufacturer and pass it a little bit to the industry so that they can start to think in our way. So this is the same equation. We've talked about it. Possibly in 2023, we can cover waveform, which is already partially covered in IGSE and I2GSE, and we see opportunity to do it better. Hopefully, we can add temperature into the model, which is not captured in most of the existing analytical models. There are still remaining challenge. One is the DC bias, which right now we know we have DC bias data, but we think it's still immature. So we decided not to include DC bias this year because the relationship between B and H, there's still no solid understanding, and we don't know how to precisely convert H into B for this year. And maybe in the future years, we'll figure out a way to capture it. We don't have geometry impact, both because we don't have data. Like right now, all of our data are collected for toroidal cores with similar geometry. We know that when you go with smaller core, bigger core, or E core, or other shape of core, the core loss can be very, very different, and we're not ready to capture that. And perhaps in the future, if we want to touch finite element modeling, there's a way to say, well, instead of really go with empirical methods for the geometry impact, maybe there's a finite element modeling approach which can partially cover geometry impact, so that's saved for future years. There's also one remaining question about high frequency magnetics. Right now, we only cover up to 500 kilohertz. So maybe in the future, it's actually still an open question. If we really start to create a community, maybe we can develop better core loss measurement methods at high frequencies. On the right-hand side, I'm showing the on-chip magnetics, sort of like a motivation why we need precise models, because if you want to put magnetics on chip, then every cubic millimeter matters, and its cost, its performance, its thickness. So we are reaching a point where we need better, more precise understanding about magnetics. Any question? Any thoughts? Yeah, I already start to see a few questions here. Maybe we should pause and try to answer the question a little bit. So I see the first question from Matthew. Hello. Indeed, much, if not all, of the scientific theories developed over the span of our civilization are inherent approximation of the real-world scenario. We're unable to understand the universe itself, but we create accurate models based on information tools available to us. I believe that, in fact, this is a case due to a combination of things, along with the lack of general interest. Based on the research I've done so far, this is especially true for the stem equation, which now is being impact color. Sorry, this question is very long. I have to read. What is it exactly about? I think the first question is basically a comment saying that we have all the complex things going in the real world, and now we need better models, and machine learning could be a good tool. And I agree with that. I think there will be a winning team who really develop a better understanding from the machine learning side, and we highly encourage that. But while you are developing machine learning, what I want to say is that we're looking for a simplest model. You can always make a neural network big and very accurate, but end up looking like a lookup table. It's not really the model is trying to understand the physics behind it. So we hope that when you are developing new machine learning models, you try to keep it simple, try to explain it, and try to explain why a model is better than the other model, instead of just simply trying and testing all the modern tools. So if you're just simply using a modern tool, you may be overkilling the problem and not really advancing the understanding. I'll go with the next question. Chusang Li. I noticed that the existing data are all for ferrite. Will your new material for testing cover other material type, such as nanocrystalline? For this year, no. For this year, everything will be ferrite. Because that's the data we have, and we did the quality control on the data. But that being said, in future years, we do have interest in expanding to other materials, because it's very likely that different material you should model it in different ways because the physics are different. And we encourage that. So really, we hope if you have the data, or if you have the capability of developing the database for other materials, we welcome. And in the future, we do have interest in expanding to other material. The next question is, a list of members had very few manufacturers for magnetic material. What effort was made to request their participation? So the list of members right now, we have PSMA representation here. If you go to our list, so Matt Wilkowski is well respected in the industry. He leads the standard committee of IEEE PELS for magnetics for many years. So he will help us to make the connection with industry. And George Slama, who is now leading the standards committee, I believe, and he's coming from Wood Electric, and I'm sure they are looking at what we're doing. And if they see something valuable, I'm sure they will be happy to bring this to the industry. And also at Herbert, maybe many of you have seen his slides online, and all the we do have members carrying the legacy of the industry and have capability of reaching out to industry. So, well, on the other hand, if you come from industry and you want to join us, reach out to me, and I'll be very happy to try to make connections and really listening to what does the manufacturer has to say on this aspect. One thing which we believe is definitely true is manufacturers has a lot of data and they have their own understanding of materials. But one thing is that because of business reasons, they don't want to share the information, or there are other risks. And the other thing with what's happening in the industry, based on what I know, is that it's very hard to control the quality or consistency of the data because people may join the company, may leave. The data may be there for many, many years, and it's not controlled in a similar way. So that's why we see that academic-driven initiative could be very, very useful, because we can keep everything consistent and we can keep everything trackable. And we're not afraid of our material, one material is worse than the other material. Well, if you are a manufacturer, you do have the concern that if I publish the data, my material is not as good as other materials, what do we do? But from our perspective, we'll be happy to keep everything transparent and open. And it'd be great if industry can feed information to us, but we'll be happy if some of the information or knowledge end up being transferring to industry. I hope this answers your question. Then the next come from Matthew. So question regarding academic industry collaboration. Based on rules, from what I understand, this challenge is to student branch and university-based groups. However, to expand the community, maybe we should have industry members. So what would be the best approach to become a potential collaborator? So yes, so we don't want, we make this competition as a student challenge because we don't want a software company coming and then with a lot of resources and then sort of crashing all the other opportunities. So we hope that this could be a student-driven competition where everything's driven by curiosity and interest. So that's the limitation. Well, on the other hand, well, we probably should have some of these big companies coming in just to have the intention to win. So we'll keep this open as a possibility. Maybe in future years we can sort of set up a different track where companies can come in and also compete. That'll be very interesting. But for now we'll keep it as a student competition, and industry members can join and be an advisor. You can work with the student and you can provide all your insights and even data. Like we say in the handbook that we provide data for 10 materials, but you are welcome to use whatever data, whatever knowledge you can find, even if it is private, to train your model. Like your model is trained by your private data, but now can offer much better performance than that. We're open to that. It's okay. Anything the panelists want to add for these questions? I guess you guys can also see all these questions.
Yeah, I thought maybe I would just read the next question to give you a break from doing all the reading here.
Okay.
So the next question is access to data and information for teams wanting to participate. How will this be handled for each approach?
So the data are all available on the MagNet website, or you can go to this link on the bottom of the page. Right now it's hosted at Princeton under my group's website, Minji/MagNet, and you can download all the data either from our MagNet database online, or there's a Dropbox link provided on this webpage, and you can download from there. So right now we have data for 10 materials under all kinds of operating conditions, waveform, frequency, and temperature, and you can download all of them. We also have raw data. So the data we made it available for download is a single cycle data, which we process it. But if you all have interest in getting the raw data, I believe you can download it from online, and we'll be happy to provide it to you. In terms of model, we have created a few tutorial neural network models that you can learn from and using as a starting point. And Professor Sullivan and Tom has also developed a equation-based model with all the software implementation, and I believe Tom has also open sourced it. So feel free to reach out to us if you see any difficulty in getting access to the data.
And there was another question that says, are you going to comment on the data structure today? And maybe getting into the full details of that is something that we'll do in a future webinar?
We can, depending on the time. So right now we have like 10, 15 minutes left. So I'll be happy to get into that if there are sufficient interest. But let's try to answer all the questions first.
Okay, and another question on the structure of the competition is, are cross-institution based teams an option for this competition?
We thought about that. I think yes. We welcome cross-institution because we hope the best people can work together. So yes, if you have a need, with the form you can only fill it one, but if you have a need, and there are also requirements, I will get to that. That's probably very important. On the handbook, we write as we only host one team from one university. This is based on consideration. We're worried that in the end we have to handle 5,000 teams, 500 teams. That's too much. So we try to set a limit. But right now, let's see. Like if there are multiple teams from one university want to participate, let us know, and we'll try to host as many teams as possible. So our philosophy, as I said, we try to reduce the entry bar as much as possible. I think honestly, our capability of hosting maybe 100 teams, maybe, I don't know. And that really depends on how many teams are seriously doing the real work. So I would say we put the one team per university there just as a limit. But if you have interest or if things happen, let us know and we'll make it happen.
I think the question was actually asking the reverse, not
Yes.
2 teams per university, but 2 universities per team.
Yes, but then there could be multiple people from multiple universities. I'm thinking that way. So if we open this, then there could be 2 or 3 teams jointly between many universities. Then basically our rules becomes voided. There's no rule anymore. We can't limit the overall number of teams. So what I can say is let us know. Don't think the team number limits or the team format limits as a real hard constraint. Let us know and we'll make our best decision. Our philosophy is to host as many teams as possible.
So Minji, if I may add to this, I think the cross-institutional teams, I think we might actually want to encourage rather than say, oh, I don't know, I know you have some practical limits in terms of the number of teams. I'm not sure having cross-institutional teams is necessarily going to blow up the numbers.
Mm-hmm.
But why not? I mean, this sounds like a great opportunity for people to connect across institutions and have less of the institution-based kind of competition and more competition in terms of innovation and however you can team up. I guess that would be my opinion on the cross.
Yeah, I agree. I think I'm very open on this. It's only like in the end how many teams we have to evaluate, but I think that's a good trouble to have. We should be able to find sufficient expert to help us reviewing. So yes, so I would say as Professor McNally said, let's encourage. And that's an advantage of this virtual software competition is that you don't have to be physically co-located.
Okay, and let's take some of the more technical questions. There's a question of does the measured data provided consider the saturation effect? And my answer to that is that the data provided is really the actual data of what happens with these excitations. So if there is saturation going on at the particular excitation level, then that is included, the effect of that is included in the data that you see. It's because we're not including DC bias in this iteration, there's less often saturation. So you won't have saturation with DC bias with a small drive level, but the data that has a large drive level, whatever saturation is there is in that data.
What we do not have is like measurement very deep into the saturation, because also practically we are typically not driving ferrites deep in the saturation, but like Professor Sullivan said, saturation is intrinsically included in the measurement. We just don't have really measurement very, very far away in the saturation.
Right. Yeah, we don't really differentiate saturate or not saturate because it's not like 0 and 1. So we do have data that is a little bit saturated. So it's just the raw data you get.
Okay, and there's another question that says, why magnetics? It takes more time to stabilize its temperature. And so I think there may be two parts to that question. Why magnetics is really because magnetics is hard. And if we said we're going to model something else that's easier, yes, that would be easier, but it's not so much a problem that's unsolved that needs work. So it's really the fact that it's hard that motivates us to do this. And then there's also the question of time to stabilize the temperature. So that gets more into the data collection method. And the approach that we are using in general is that we have the cores in an oil bath, and that oil bath sets the temperature of the core. And as we excite it, it will warm up, but we do that with a low enough duty cycle and with enough pauses to make sure that it doesn't go beyond that. Don't go too much outside of that initial oil temperature, but that is one of the limitations of the data, and that's one of the error sources, and there is some documentation about that. I don't know, does anyone want to add more detail there? Or maybe we should circle back to that if people have follow-up questions about it.
Mm-hmm.
Another question is whether the data is available to people who aren't actually going to field a team and enter the competition this year. And the answer is yes, this is open data. It's all at that website, available to anybody.
Yes.
No need to register or anything. It's just there. And another logistical question is on team formation. What date is the basis for determining whether the status is undergrad or grad student status? And I'm not sure we have an answer to that one.
No, I think it could be very tricky depending on the school systems in different country. So I would say submit your registration and we'll try to host as many teams as possible. Our goal is that you should before you submit you should be in student status when you are submitting a model. I think that's the baseline. As long as you are in student status, as long as it's not like full undergraduate team or full graduate team, like we do have a motivation of having a combination of undergrad and grads because educating undergrads is part of the mission of IEEE. So we do hope that it's a mix of undergrad and grad, and you can split the jobs and tasks and then share the knowledge. But on the other hand, there are some rules, but we won't. If it's tricky or on the fence, we'll try to accommodate what's needed.
Okay, and another technical question is capacitive effects of the winding. Are they also included in the measurement, especially for high DDT excitations, because that may impact the measurements? So yes, a very excellent technical question. Who wants to take that?
Charlie, do you want to take that? Or I can take that. Or maybe Diego can take that. Oh, Diego already.
Okay.
Tom can talk about that.
Okay, we are trying to remove, the goal of the measurement is to measure the core material. So the goal is to remove as much as possible the impact of the winding, both the winding losses, but also the capacitive effect. The fact is, it is never possible to completely remove the impact of the capacitance, especially very difficult to really assess the impact of the capacitance because at high frequency, the core material itself becomes capacitive. So it is very difficult to say, are the capacitive effect coming from the material itself, or are they also coming from the winding? So the baseline is we are trying to make the winding such that the capacitance, or also the capacitance of the current measurement system, is as low as possible. But of course, we cannot completely remove the impact of the winding capacitance in the measurement. And for the dividity, yes, this is something that is not currently in the dataset. We don't have different dividity, but as Minche said, we are also providing the raw data, so you can really look at the waveform and look at which dividity there is exactly this measurement. So you can basically decide if you want to use this information or you prefer to basically ignore it, because it has an impact, but it's not the main impact on the core losses.
Right. The way I look into this is like the way we're running it. We provide data and modeling are done by different people. This separate the challenge a little bit. Sort of, if we have better data right now, we cannot say that our data is completely free of capacitive effect. But on the other hand, in a real design, you always have some jointly existing capacitive effect in the system. And if you develop model based on data driven, if someone else next day or next month or next year give you better data, then a good methods, which is generalized or maybe based on real true physics, should be able to quickly adapt to the better data and develop better models. So I would say, yes, there are challenges in this, but we are trying to address all of these as a community.
Okay, I'm trying to see what questions we haven't gotten to yet. There are a couple of comments. Ed Herbert comments that the PSMA Dartmouth core loss data is also available to anyone. It's limited to 80 degrees C, but includes many low duty ratio examples. So maybe we can also make sure that people know where to find that data if they're interested in just gathering more data and using that as well. We have a suggestion from Jose Cobos to provide VI in addition to BH. And I think someone want to comment on that?
Yeah, so V and I, when it comes in, then we are bringing geometry in here. And whenever we talk about geometry, we are getting into error. So we have been very careful in not getting into components, but stay on the material. So maybe BNH is more of a material level behavior, and VNI is more of a component level behavior. And there are errors in translating V to B and I to H and between the two and back and forth. And we try to not doing that, at least for this year. So that's why we sort of try to just stick with B and H. But in the future, we see the possibility. Well, VNI data are available. If you are interested in using VNI, you can go to our website and download from there. And if you can't find it, we can show you where they are. But this year we try to focus on material and we try to not get into geometry. That will be my answer.
Yeah. So, yeah, and certainly in terms of how you formulate your model, there's a integral derivative relationship between voltage and B, as well as the geometry and number of turns relationship. And yeah, if you find that your model works better on the derivative of B rather than on B directly, absolutely, there are lots of transformations of the data that you can do, and some of those may be advantageous, and we don't want to prejudge which of them will work best. I think the only question that we haven't addressed here is that the list of members had very few manufacturers of magnetic materials. What effort was made to request their participation? I think the general answer there is that if there are manufacturers of magnetic materials that want to get involved, we would love to have that participation and interaction.
Yes. And even data, like maybe there are a few manufacturers who's willing to share the data, and that's great. And we'll be happy to transfer the data to the student teams and figure out a way to share the data in a good way.
Okay, so that's all the questions that I'm seeing here. People are welcome to submit more questions. Minji, was there more that you wanted to talk about?
Yeah, let me quickly go through it. I think I talked about most of the things already. So just the rules of the competition. So we'll have 3 inputs. One is the waveform, 1024 step waveform describing how the shape of the bee look like, and frequency and temperature. And we only look for a single floating number output. That's the volumetric core loss. You may choose to downsample the 1000 steps because that's probably too much, but just as one of the comments saying DVDT is very important, or DBDT is very important. So maybe there are good reason to go with high resolution in describing a waveform, but the downside is that your model will be bigger. So we do look forward to see innovative ways to detecting the high DBDT region and maybe downsample the data a little bit so that your model gets smaller, or some pattern recognition of the waveform saying, well, I'll be focusing on this transition because that's very important in terms of determining my core loss. So we are open to all kinds of innovation for you to implement within the algorithm. You can downsample the data to reduce your model size, but probably you're paying a little bit more on accuracy. And we are, as I said, we're looking for a simple model, but can get reasonably good accuracy. And then which team will win in the end is determined by our judging committee. Yeah, that's the competition rule. Well, this is sort of saying the same thing. We have very simple model that is statement equation, very explainable, give us really good insights. We have very complex model. We provide it as a baseline. Right now it has like 10,000 parameters, and there's a huge room in between. We're looking for a solution or many solutions, trying to approach this from different angle with trade-offs. And maybe have smaller parameter size, because if you have lower number of parameters, you need less number of data to train it. So it could be 2 aspects. We're looking for a better model structure, simpler, explainable, better, and less model parameter. So we hope that representing one magnetic material, if you can use 10 parameters to represent a material, that is better than if you have to use 100 parameters to representing a material. And where's the balance is the student team's choice. So this is the data flow. We will be providing a large amount of measurement data, and then you can evaluate the data complexity and selecting the model strategy, and then either choose equation-based models, data-driven models, or combination of them, or any innovative ideas you may have. And ultimately, what we're looking for is a callable MATLAB or Python function, which you can just feed an input and provide an output. And we will first evaluate your output to select perhaps the top 10 team, which give us the accurate prediction. And then we'll look into what's inside of the black box to understand what you do and the novelty of the methods. So ultimately, you will submit the prediction results. We'll give you input information and you give us prediction results. And we'll compare your prediction results with the measurement result to judging which model seems to be more general and reaching a balance between accuracy and generality. And then for the winning teams, a few teams will really carefully do a code review and understanding what you do in software and how do you implement everything. And does the model make sense, or does the method sort of has innovative insights there? So you can run this loop yourself. Like we have 10 materials. You can easily segment the 10 material into 8 materials I'm using for training, and I'm pretending that I don't know anything about the 2 material, use it for testing, because ultimately we will give you other materials which is beyond the 10 for the testing. You can set up these testing scenarios to test your understanding or test your algorithm's generality. You can also, for a particular material, you can also say, I know 60% of the data, I use 20% of the data for verification, and I have another 20% reserved, pretending that I don't know anything about it, and then you try and report the accuracy on those data. So you can, based on the 10 material, you can set up all these testing scenarios to evaluate the accuracy and generality and explainability of your model. Yeah, so a little bit about timeline, which is very important. So we're doing this online Q&A session. We are officially announcing this competition. What we're looking for is a one-page letter of intent. And actually, based on the discussion today, I'll probably revise it a little bit, but you can use the old one if you already have a team. So we'll probably relax the university constraint a little bit. I think it's a really good recommendation in relaxing that and allowing remote collaboration. That is great. And there will be a 2-page proposal due in June 1st. And the purpose of that is not trying to filter teams. It's just trying to make sure every team's serious. We don't want teams which is listed, registered, but not doing anything. So just give us some basic ideas to show that you're understanding the problem we're trying to solve and some of the preliminary idea that you're trying to try. And that's enough for the 2-page proposal. We're not really trying to look for a fully completed ideas or polished concepts. So it could be just like showing that you're understanding what we're doing here. And July 1st, we'll notify the acceptance. Basically, we'll nail down how many teams we are hosting. And as I said, we'll try to host as many teams as possible. So encourage everyone to participate, because honestly, we don't think this will be a lot of cost to evaluate a lot of algorithms, because everything can be automated. But we also don't want to run into the situation where there are just too many teams and you feel like you're not well supported. We hope that we can work closely with you, and we're really learning from each other, including our organizing committee. And all of us, you can probably feel that all of us are excited and we want to learn what method seems to be the best method. So November 1st you all be submitting your model for the 10 material. So for the 10 big existing database, and you can model them and model the 10 material. And at the same time, we will give you a little bit of a new data for 3 different material, which is similar. 3 similar but different materials. And we'll give you a small amount of data, both including the input information and output information, so that you can fine-tune your model. And we will also give you a lot of input data without the output, and you will have to submit your output, predicted output from your algorithm, and we'll evaluate the model performance based on your output and compare it to our reference. And the winning teams, we will look deeply into the code, and we probably will also reach out to you, and maybe you need to put together a brief presentation to tell us what you do within the model, and then we can verify and really select the final winner. And the goal is that hopefully we can wrap everything up early next year, and we can announce the winner around APEC time, and the winning teams will be invited to one of the future conferences, either at APEC or ECCE or design methodology conferences or Compel. So it could be one of the prominent power electronics conferences, and we announce the winners there, and you'll be invited to give a presentation, and we'll help you to probably implement your algorithm to be a better way. We also have a software engineering award, where if a team has a really good software talent and build a software tool that is very, very flexible and expandable and very useful, we will try to build a sort of open source Python or MATLAB model that everyone can download and use. And perhaps that can be a replacement of the statement equation or datasheet for the 10 materials that we already have, or even the 3 materials we add. So ultimately, at the end of this year, end of the competition, we probably hopefully will have a callable function for 13 materials, which is great achievements already. Yeah, that's the timeline. But
sorry, yeah, just as a quick follow-up, because there are 2 questions that are closely related to what we just introduced. The first one, they asking like, can we use other programming languages besides the MATLAB and Python?
The answer is no. I think you can do almost everything with MATLAB and Python, and going to a different language will make our job very difficult. So that's constraint or limit to Python and MATLAB. And maybe if you don't know Python or MATLAB, learn Python and MATLAB, which is very, very useful.
There is a comment about MATLAB and Python being very slow, which is very true. However, you are welcome to leverage external library. Like if you are using Python, you are welcome to use numerical Python or the Fortran BLAST library, or to use neural network libraries such as PyTorch or TensorFlow, which are running on GPU. So basically, Python, your code should be in Python or in MATLAB, but you are welcome to leverage high-performance computing library, which are way more optimized than raw Python code if you are concerned about implementation speed.
Right. And the other thing which we're thinking about is depending on how many teams we end up having, if it is capable, we still have budget. And if it is capable, and if we are within the budget, we may be able to offer free Google Colab access. And actually, Google is funding this competition. So we will, depending on how many teams we get, we probably will have the capability of providing like better cloud services, cloud computing service to you.
Yes, exactly. And another question also quite related, like what will be the basic material description? Like will the material be taken as one of the input of the model? So from my perspective, I think like this depends whether you are using equation-based model or like neural network models. For equation-based model is essentially for different materials, you will have different sets of parameters. And for neural network, it depends whether you want or maybe don't want to use the material as one of the input. If you want, you can use that label, or you can have different models. This is what I think.
So what we're thinking is really what we're asking you to submit is a callable function. So if you want to program your callable function with the material label as an input, that's doable. Or if you submit 10 functions to us, and each function is mapping to a material, and that's okay. So it's your decision. You can have a general framework and then just calling different parameters. Or you can have just separate function. We do look for better coding, so you should comment your code and then really tell us how to use it. If you can tell us how to use it, you'll be okay. Well, the bottom line is that we will have to, you want to make sure a third party, which is very important for open source anyways, is that you want to make sure other people can understand your code and make use of your algorithm. So it's your responsibility to make your code readable and usable.
Okay, I think we answered every question. Are there any others? Okay, I don't think so. Thank you so much, Minji, and the rest of the panelists. You guys did an amazing job. As a reminder, information on how to request a PDH certificate has been sent to you via the chat function and will also be included in the follow-up email you'll receive within 1 hour of completion of this webinar. For any information on upcoming Pels webinars, please visit our website. This concludes today's webinar. Thank you so much for attending and have a great day.
Thanks, everyone. Feel free to send us an email if you have any question about anything.
Great. Thank you. Bye-bye, everyone.
Bye.
Thanks. Bye.